Hello, ladies and gents. Welcome to another episode of ML for Noobs. Now, this time, what I want to do is I want to take a bit of a pause from the Ryan videos, the Which Ryan Is It video series, and try and see if there's actually something that we haven't learned that might help us a lot in that exercise. And so I've already made a post on the FastAI forums, and I'll try to see why we're not getting the sort of results that we were expecting. High accuracy results. There were a lot of failure modes that we covered in the previous videos, and so we will figure out what is going on with those, with that specific application. Maybe there's a setup thing. Maybe it's something that we haven't actually taken yet, and so telling the difference between a grizzly bear and a teddy bear is very different than telling, the difference between two faces that are largely similar but have some discrepancy. So we'll get back to that. We're definitely not forgetting about it. We're going to get back to it. But I feel like it's probably a good idea to go through the rest of the lessons, know what we don't know, and then come back to it with more knowledge and be able to come up with specific solutions to problems that we might not even know we have today. All right. So that said, let's jump right into the video series and continue from whence we left off. So Jeremy, it's good to see you again. For the record, we're at lesson 3. We just finished data blocks. We're looking at multi-label classification. All right, take it away, Jeremy.
So they're the steps. I mean, we invented this API. I don't know if other people have independently invented it. The basic idea of kind of a pipeline of things that got into each other is pretty common in a number of places. Not so much in Python, but you see it more in JavaScript. Although this kind of approach of like each stage produces something slightly different, you tend to see it more in like ETL software, like extension transformation and loading software, where there's kind of particular stages in the pipeline. So yeah, I mean, it's been inspired by a bunch of things. But all you need to know is kind of use this example to guide you, and then look up the documentation to see which particular kind of thing you want. And in this case, the image file list, you're actually not going to find the documentation of the image file list in data blocks documentation because it's specific to the vision application. So to then go and actually find out how to do something for your particular application, you'll then go to look at text and vision and so forth, so you can find out what are the data block API pieces available for that application. And of course, you can then look at the source code. If you've got some totally new application, you can create your own part of any of these stages. So pretty much all these functions are, very few lines of code. Maybe we can look at an example of one. Image list from folder, so that's under temporary, and then we're going to go t.label from CSV. Then you can look at the documentation to see exactly what that does, and that's going to call label from data frame. So I mean, this is already like useful. Like if you wanted to create a data frame, append this data frame from something other than CSV, you now know that you can actually just call label from data frame. You can look up, define what that does, and as you can see, like most fast AI functions are no more than a few lines of code. They're normally pretty straightforward to see what are all pieces there and how you use them. And it's probably one of these things that as you play around with it, you'll get a good sense of how it all gets put together. But if during the week there are particular things that you're thinking, I don't understand how to do this, please let us know, and we'll try to help you. Sure.
What resources do you recommend for getting started with the video, for example, whole frames and submit them to your model?
I guess the answer depends. If you're using the web, which I guess probably most of you will be, then there's web APIs that basically do that for you. So you can grab the frames with a web API, and then they're just images which you can pass along. If you're doing it client side, I guess most people are going to use OpenCV for that, but many people during the week who are doing these video apps would tell us what have you used, found useful, and we can start to compare something in the lesson wiki with a list of video resources. Sounds like something very interesting. Okay, so just like usual, we unfreeze our model, and then we get some more, and we get down to 9 to 9-ish. So one thing to notice here is that where before we unfreeze, you'll tend to get this shape pretty much all the time. If you do your learning rate find before you unfreeze, it's pretty easy. Find the steepest slope, not the bottom. Right? Remember, we're trying to find a bit where we can slide down it quickly. So if you start at the bottom, it's just going to send you straight off to the end. So somewhere around here, and then we can call it again after you unfreeze, and you'll tend to get a very different shape. Right? And this is a little bit harder to say what to look for because there tends to be this kind of shape. You get a little bit upward and then kind of very downward and then up here. So I tend to kind of look for just before it shoots up and go back about 10x. Right, as kind of a rule of thumb, so 1 in negative 5. Right? And that is what I do for the first half of my slice. And then for the second half of my slice, I normally do whatever learning rate I used for the frozen part, so LR, which was 101, kind of divided by 5, or divided by 10, somewhere around that. So that's kind of my rule of thumb, right? Look for the bit kind of at the bottom, find about 10x smaller, that's the number that I put here, and then LR over 5 or LR over 10 is kind of what I put there. It seems to work most of the time. We'll be talking more about exactly what's going on here, so what discriminative learning rates as the course continues. So how do we get this better than 929? Because there are how many people in this competition? About 1,000 teams, right? So we want to get into the top 10%. So top 5% would be 0.931-ish. Top 10% is going to be about 929-ish. So we're not quite there. Right? So here's the trick, right? I don't know if you remember, but when I created my data set, I put size equals 128. And actually the images that Kaggle gave us are 256. So I used the size of 128 partially because I wanted to experiment quickly. It's much quicker and easier to use small images to experiment. But that's the second reason. I now have a model that's pretty good at recognizing the contents of 128 by 128 satellite images. So what am I going to do if I now have a model that's pretty good at 256 by 256 satellite images? Well, why don't I use transfer learning? Why don't I start with a model that's good at 128 by 128 images and fine-tune that? So don't start again, right? And that's actually going to be really interesting because if I'm trained quite a lot, if I'm on the verge of overfitting, which I don't want to do, right? Then I'm basically creating a whole new data set effectively, one where my images are twice the size on each axis, right? So 4 times bigger. So it's really a totally different data set as far as my convolutional neural network is concerned. So I kind of going to lose all that overfitting. I get to start again. So let's create a new learner, right? Well, let's keep that same learner, but use a new data bunch, where the data bunch is 256 by 256. So that's why I actually stopped here, right before I created my data sets. Because I'm going to now take this data source, and I'm going to create a new data bunch with 256 instead. So let's have a look at how we do that. So here it is. Take that source, right? Take that source, transform it with the same transforms as before. This time use size 256. Now that should be better anyway, because this is going to be higher resolution images. But also I'm going to start with, I haven't got rid of my learner, it's the same learner I had before, so I'm going to start with this kind of pre-trained model. And so I'm going to replace the data inside my learner with this new data bunch. And then I will freeze them, so that means I'm going back to just training the last few layers. And I will do a new LR find. And because I actually now have a pretty good model, like a pretty good for 128 by 128, so it's probably going to be like at least okay for 256 by 256, I don't get that same sharp shape that I did before. But I can certainly see where it's way too high. Right? So I'm going to pick something well before where it's way too high. 10 maybe 10x smaller. So here I'm going to go 1 e, 2, 1, 2. It's 10's well before it shoots up. And so let's fit a little bit more. Okay, so we froze it again, so we're just training the last few layers, fit a little bit more. And as you can see, I very quickly, remember kind of 928 is where we got to before after quite a few epochs. So we're straight up there, and suddenly we've passed 0.93. Right, so we're now already kind of into the top 10%. So we've hit our first goal. Right? We're at the very least pretty competent at the problem of recognizing satellite imagery. But of course now, we can do the same thing before. We can unfreeze and train a little more. Okay, again, using the same kind of approach as before, allow it 5 here, and the small one here, train a little bit more, 0.9314. So that's actually pretty good, 0.931. Somewhere around top 20-ish. So you can see actually when my friend and I entered this competition, it came 22nd with 0.935. We spent this a year or two ago, months trying to get here. So using kind of pretty much default with some minor tweaks and one trick, which is the resetting tweak, you can kind of get right up into the top of the leaderboard of this very challenging competition. Now, I should say, we didn't know where we would be. We actually have to check it on the test set and have a us and actually speak to the competition, particularly the exhibition. And so later on in the course, we're going to do that. But we certainly know we're doing well. We're doing very well. So that's great news. And so you can see also as I kind of go along, I tend to save things. You can name your models whatever you like, but I just want to basically know, is it kind of before or after the unfreeze, let's take 1 or 2, what size were they training on, what architecture was they training on. So that way you can always go back and experiment pretty easily. So that's kind of body-label classification. Let's look at another example. Another the other example next we're going to look at is color, or tree
folks,
building pixels the same color.
got disconnected
now,
for a
we're not
bit,
actually
but let's keep going.
We're actually going to do it where each of those pixels has a unique number. So in this case, the top left is building, so this building is number 4, top right is trees, so tree is 26, and so forth. Right? So in other words, this single top left pixel, we're basically going to do a classification problem, just like the text classification, for the very top left pixel. We're going to say, what is that top left pixel? Is it bicycle, road lines, sidewalk, building? What is the very top left pixel? And then, what is the next pixel on? What is the next pixel on? So we're going to do a little classification problem for every single pixel in every single image. So that's called segmentation. Right? In order to build a segmentation model, you actually need to download or create a data set where someone has actually labeled every pixel. So as you can imagine, that's a lot of work. Okay? So this is so that's going to be a lot of work. You're probably not going to create your own segmentation data sets, but you're probably going to download or find them somewhere else. This is very common in medicine, life sciences. If you're looking through slides, nuclei, it's very likely you already have a whole bunch of segmented cells and segmented nuclei. If you're radiology, you probably already have lots of examples of segmented lesions and so forth. So there's a lot of kind of different domain areas where there are domain-specific tools for creating these segmented images. As you could guess from this example, it's also very common in kind of self-driving cars and stuff like that, where you need to see what objects are bound and where are they. So in this case, there's a nice data set called Canvid, which we can download, and they have already got a whole bunch of images and segment masks prepared for us, which is pretty cool. And remember, pretty much all of the data sets that we have provided kind of inbuilt URLs for, you can see their details at course.fastly.ai/datasets. And nearly all of them are academic data sets where some very kind people have gone to all this trouble for us so that we can use this data set and made it available for us to use. So if you do use it, one of these data sets for any kind of project, it would be very, very nice if you were to go and find the citation and say, thanks to these people for this data set. Because they've provided it, and what they're asking in return is for us to give them that credit. Okay, so here is the Canvid data set, here is the citation, and on that data set page, that will link to the academic paper where it came from. Okay, Rachel, now it's a good time for a question.
Is there a way to use learn.lr find and have it return a suggested number directly rather than having to plot it as a graph and then pick a learning rate by visually inspecting that graph? And there are a few other questions if there are more guidance on creating the learning rate from your graph.
Yeah, it's a great question. The short answer is no. And the reason the answer is no is because this is still a bit more artisanal than I would like. As you can kind of see, I've been kind of saying how I read this learning rate graph depends a bit on what stage I'm at and kind of what the shape of it is. I guess like when you're just training the head, so before you unfreeze, it pretty much always looks like this, and you can certainly create something that kind of creates a slightly, creates a smooth version of this, finds the sharpest negative slope, and pick that, you'll probably be fine nearly all the time. But then for these kinds of ones, it requires a certain amount of experimentation. But the good news is you can experiment, right? You can try. Obviously, if the line's going up, almost certainly at the very bottom point, you don't want it, right? Because you need to be going downwards. But if you kind of start with somewhere around 10x smaller than that, and then also you can try another 10x smaller than that, try a few numbers, find out which ones work best. And within a small number of weeks, you will find that you're picking the best learning rate most of the time. Right? So I don't know. It's kind of, so at this stage, it still requires a bit of playing around to a sense of the different kinds of shapes you see and how to respond to them. Maybe by the time this video comes out, someone will have a pretty reliable auto learning rate finder. We're not there yet. It's probably not a massively difficult job to do. Interesting project. Collect a whole bunch of different data sets, then you grab all the data sets from our data sets page, try and come up with some simple heuristic, compare it to all the different lessons I've shown. That'll be a really fun project to do. But at the moment, we don't have that. I'm sure it's possible, but we have fun. Okay, so how do we do image segmentation? Same way we do everything else. And so basically, we're going to start with some path which has got some information in it of some sort. So I always start by uncovering my data, do an ls, see what I was given. In this case, there's a folder called labels and a folder called images. So I'll create paths for each of those. We'll take a look inside each of those. And at this point, you can see there's some kind of coded file names for the images and some kind of coded file names for the segment masks. And then you kind of have to figure out how to map them one to the other. Normally, these kind of data sets are kind of a README you can look at, or you can look at their website. Often it's kind of obvious. In this case, I can see these ones always have this kind of particular format. These ones always have exactly the same format with an underscore p. So I kind of, when I did this on Status Guest, I thought, oh, probably the same thing, underscore p. And so I created a little function that basically took the file name and added the underscore p and put it in a different place. And I tried opening it, and I don't see it. So I created this little function that converts from the image file names to the equivalent label file names. I opened up that to make sure it works. Normally, we use open image to open a file, and then you can go to show to take a look at it. But this, as we described, this is not a usual image file. It contains integers. So you have to use open mask rather than open image because we want to return integers, not floats. And FastAI knows how to deal with masks. So if you go mask.show, it will automatically color code it for you in some appropriate way. That's very set open mask. So we can kind of have a look inside, look at the data, see what the size is. So there's 720 by 960. We can take a look at the data inside, and so forth. The other thing you might have noticed is that there's a file called codes.txt and a file called valid.txt. So codes.txt, we can load it up and have a look inside, and not surprisingly, it's got a list telling us that, for example, number 4 is 0, 1, 2, 3, 4. It's building, top left is building. There you go. Okay? So just like we had, Grizzly, like there's teddies, here we've got the coding for each one of these pixels.
Okay, so I'm going to try and predict what's going on here. So he's saying that segmentation is effectively the same as what we were doing earlier with classification, but the only difference is that you need to make a decision on every single pixel. So you need to look at every single pixel and determine or estimate what the outcome is going to be, which sounds crazy because I'd imagine every pixel is dependent on the pixel before that, right? So there's some sort of sequence that you need to run this in, and so I'd like to see how that actually works. At the same time, though, it's not very different from character recognition or number recognition with the MINS data set, right? Also, the pixel after that depends on the pixel before that, right? So when you have a line, you want to do edge detection. Edge detection is effectively lumping together pixels that are dependent on their adjacent pixels. So yeah, it kind of makes sense high level, but if you're making decisions at the pixel level, yeah, I mean, let's see how this actually works. I mean, my guess would be okay, like the same idea that we had previously could work with this sort of thing, and really it's just a matter of syntax, like figuring out what the syntax is going to look like when you're trying to run this exercise.
So to create a data bunch, we can go through the data block API and say, okay, we've got these image files, they're in a folder. We need to create labels, which we can use with that get y file name function we just created. We then need to split into training and validation. In this case, I don't do it randomly. Why not? Because actually, the pictures they've given us are frames from videos. So if I did them randomly, I would be having two frames next to each other, one in the validation set, one in the training set. That would be far too easy. That's treating. Right? So the people that created this data set actually gave us a data set saying, here is the list of file names that are meant to be in your validation set. And they're non-contiguous parts of the video. So here's how you can split your validation and training using a file name file. So from that, I can create my data sets. And so I actually have a list of class names. So often with stuff like the planet dataset or the pets dataset, we actually have a string saying, this is a pug, or this is a ragdoll, or this is a vermin, or this is cloudy, or whatever. In this case, you don't have every single pixel labeled with an entire string. That would be incredibly inefficient. They're each labeled with just a number, and then there's a separate file telling you what those numbers mean. So here's where we get to tell it in the data block API. This is the list of what the numbers mean. Okay, so these are the kind of parameters the data block API gives you. Here's our transformations. And so here's an interesting point. Remember I told you that, for example, sometimes we randomly flip an image, right? What if we randomly flip the independent variable image but we don't also randomly flip this one. They're now not matching anymore. Right? So we need to tell FastAI that I want to transform the y. So x is our independent variable, y is independent. I want to transform the y as well. So whatever you do to the x, I also want you to do to the y. So there's all these little parameters that we can play with. Like create a data bunch. I'm using a small batch size because, as you can imagine, because I'm creating a classifier for every pixel, that's going to take a lot more GPU. Right? So I found a batch size of 8 is all I can handle, and then normalize in the usual way. And this is quite nice. FastAI, because it knows that you've given it a segmentation problem, when you call show batch, it actually combines the two pieces for you and it will color code the photo. Isn't that nice? Right? So you can see here the green on the trees and the red on the lines, and this kind of color on the walls and so forth. Right? So you can see here are the pedestrians, this is the pedestrian backpack. So this is what the ground truth data looks like. So once we've got that, we can go ahead and create a learner. I'll show you some more details in a moment. Call LR find the sharpest bit, which looks about 1 index 2, call fit, pass against slice LR, and see the accuracy, and save the model, and unfreeze, and train a little bit more. So that's the basic idea. Okay? And so we're going to have a break, and when we come back, I'm going to show you some little tweaks that we can do, and I'm also going to explain this custom metric that we've created, and then we'll be able to go on and look at some other cool things. So let's all come back at 8 o'clock, 6 minutes. Okay, welcome back everybody, and we're going to start off with a question we got during the break.
Could you use unsupervised learning here, pixel classification with a bike example, to avoid needing a human to label a heap of images?
Well, not exactly unsupervised learning, but you can certainly get a sense of where things are without needing these kind of labels. And time permitting, we'll try and see some examples of how to do that. You're certainly not going to get such a quality and such a specific output as what you see here, though. If you want to get this level of segmentation mask, you need a pretty good segmentation mask ground truth to work with.
And is there a reason we shouldn't deliberately make a lot of smaller data sets to step up from in tuning, let's say 64 by 64, 128 by 128, 256 by 256, and so on?
Yes, you should totally do that. It works great. Great. I found this idea is something that I first came up with in the course a couple of years ago, and I kind of thought it seemed obvious and just presented it as a good idea, and then I later discovered that nobody had really published this before, and then we started experimenting with it, and it was basically the main trick that we used to win the ImageNet competition, the Dawn Bench ImageNet training competition, and we were like, wow, people, this wasn't, not only was this not standard, nobody had heard of it before. There's been now a few papers that use this trick for various specific purposes, but still largely unknown, and it means that you can train much faster, it generalizes better. There's still a lot of unknowns about exactly like how small and how big and how much at each level and so forth. But I guess as much as it has a name now, it probably does, and I guess we call it progressive resizing. I found that going much under 64 by 64 tends not to help very much. But yeah, it's a great technique, and I'll definitely try a few different sizes.
What does accuracy mean for pixel-wise segmentation? Is it correctly classified pixels divided by the total number of pixels?
Yep, that's it. So if you imagine each pixel was a separate object you're classifying, it's exactly the same accuracy. And so you actually can just pass in accuracy as your metric. In this case, we actually don't. We've created a new metric called accuracy camvid. And the reason for that is that when they labeled the images, sometimes they labeled a pixel as void. I'm not quite sure why. Maybe it's something they didn't know, or somebody felt that they'd made a mistake, or whatever. But some of the pixels are void. And in the camvid paper, they say when you're reporting accuracy, you should remove the void pixels. So we've created an accuracy camvid. So all metrics take the actual output of the neural net, that's the input to this is what I call the input, the metric, and the target, i.e. the labels we're going to predict. So we then basically create a mask. So we look for the places where the target is not equal to void. And then we just take the input, do the argmax as per usual, just the standard accuracy argmax, but then we just grab those that are not equal to the void code, we do the same for the target, and we take them in. Okay? So it's just a standard accuracy, it's almost exactly the same as the accuracy source code we saw before, with the addition of this mask. So this quite often happens, that the particular Kaggle competition metric you're using, or the particular way your organization scores things, or whatever, there's often like little tweaks you have to do, and this is how easy it is. Right? And so, as you'll see, to do this stuff, the main thing you need to know pretty well is how to do basic mathematical operations in PyTorch. So that's just something you kind of need to practice.
I've noticed that most of the examples and most of my models result in a training loss greater than the validation loss. What are the best ways to correct that? I should add that this still happens after trying many variations on number of epochs and learning rate.
Okay, good question. So remember from last week, if your training loss is higher than your validation loss, then you're underfitting. Okay, it definitely means that you're underfitting. You want your training loss to be lower than your validation loss. If you're underfitting, you can train for longer. You can train the last bit at a lower learning rate. But if you're still underfitting, then you're going to have to decrease regularization, and we haven't talked about that yet. So in the second half of this part of the course, we're going to be talking quite a lot about regularization, and specifically how to avoid overfitting or underfitting by using regularization. If you want to skip ahead, we're going to be learning about weight decay, dropout, and data augmentation will be the key things that we're talking about. Okay. For segmentation, we don't just create a convolutional neural network. We can, but actually an architecture called UNIT turns out to be better. And actually, let's find it. Okay, so this is what a unit looks like, and this is from the university website where they talk about the unit. And so we'll be learning about this both in this part of the course and in part 2, if you do it. But basically, This bit down on the left-hand side is what a normal convolutional neural network looks like. It's something which starts with a big image and gradually makes it smaller and smaller and smaller and smaller until eventually you just have one prediction. What a unit does is it then takes that, makes it bigger and bigger and bigger again, and then it takes every stage of the downward path and kind of copies it across, and it creates this U-shape. It was originally actually created or published as a biomedical image segmentation method, but it turns out to be useful for far more than just biomedical image segmentation. So it was presented at MICI, which is the main medical imaging conference, and as of just yesterday, it actually just became the most cited paper of all time from that conference. So it's been incredibly useful, over 3,000 citations. You don't really need to know any of the details at this stage. All you need to know is if you want to create a segmentation model, you want to be saying learner.createUnit rather than create CNN. But you pass it the normal stuff, the data bunch, and architecture, and symmetrics. Okay? So having done that, everything else works the same. You can do the finder, find the slope, train it for a while, watch the accuracy go up, save it from time to time, unfreeze, probably want to go about 10 less, so it's still going up, so probably 10 less than that. So 1 in 5, comma, LR over 5, train a bit more, and there we go. Right? Now, here's something interesting. You can learn.recorder is where we keep track of what's going on during training, and there's got a number of nice methods, one of which is plot losses, and this plots your training loss and your validation loss. And you'll see quite often they actually go up a bit before they go down. Why is that? That's because you can also plot your learning rate over time, and you'll see that your learning rate goes up and then it goes down. Why is that? Because we said fit one cycle, and that's what fit one cycle does. It actually makes the learning rate start low, go up, and then go down again. Why is that a good idea? Well, to find out why that's a good idea, let's first of all look at a really cool project done by Jose Fernandez Portal during the week. He took our gradient descent demo notebook and actually plotted the weights over time, not just the ground truth and model over time. And he did it for a few different learning rates. And so remember, we had two weights. So we were doing basically y equals ax plus b, or in his nomenclature here, y equals w naught x plus w1. And so we can actually look and see over time what happens to those weights. And we know this is the correct answer here, right? So in a learning rate of 0.1, it kind of like slides on in here, and you can see that it takes a little bit of time to get to the right point, and you can see the loss improving. At a higher learning rate of 0.7, you can see that the ground truth, the model jumps to the ground truth really quickly, and you can see that the weights jump straight to the right place really quickly. What if we have a learning rate that's really too high? You can see it takes a very, very, very long time to get to the right point. Or if it's really too high, it diverges. Okay, so you can see here why getting the right learning rate is important. When you get the right learning rate, it really zooms into the best spot very quickly. Now, as you get closer to the final spot, something interesting happens, which is that you really want your learning rate to decrease, right? Because you're getting close to the right spot, right? And what actually happens? So what actually happens is, I can only draw 2D, sorry. You don't generally actually have some kind of loss function surface that looks like that. Remember there's lots of dimensions, but it actually tends to kind of look like bumpy, like that, right? And so you kind of want a learning rate that's like high enough to jump over the bumps, right? But then once you get close to the middle, once you get close to the best answer, you're not going to be just jumping backwards and forwards between bumps. So you really want your learning rate to go down, so that as you get closer, you take smaller and smaller steps. So that's why it is that we want our learning rate to go down at the end. Now this idea of decreasing the learning rate during training has been around forever, and it's just called learning rate annealing. But the idea of gradually increasing it at the start is much more recent, and it mainly comes from a guy called Leslie Smith. If you're in San Francisco next week, actually you can come and join me and Leslie Smith. We're having a meetup where we'll be talking about this stuff, so come along to that. What Leslie discovered is that if you gradually increase your learning rate, what tends to happen is that actually what tends to happen is that loss function surfaces tend to kind of look something like this. Bumpy, 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 flat, bumpy, 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 something like this, right? They have flat areas and bumpy areas. And if you end up in the bottom of the bumpy area, that solution will tend not to generalize very well, because you found a solution it's good in that one place, but it's not very good in other places. Whereas if you found one in a flat area, you probably will generalize well, because it's not only good in that one spot, but it's good kind of around it as well. If you have a really small learning rate, it'll tend to kind of plod down and stick in these places, right? But if you gradually increase the learning rate, then it'll kind of like jump down, and then as the learning rate goes up, it's going to start kind of going up again like this, right? And then the learning rate now going to be up here, it's going to be bumping backwards and forwards, and eventually the learning rate starts to come down again, and so it'll tend to find its way to these flat areas. So it turns out that gradually increasing the learning rate is a really good way of helping the model to explore the whole function surface and try and find areas where both the loss is low and also it's not bumpy. Because if it was bumpy, it would get kicked out again. And so this allows us to train at really high learning rates, so it tends to mean that we solve our problem much more quickly and we tend to end up with much more generalizable solutions. So if you call plot losses and find that it's just getting a little bit worse and then it gets a lot better, you found a really good maximum learning rate. So when you actually call fit one cycle, you're not actually passing in a learning rate, you're actually passing in a maximum learning rate. And if it's kind of always going down, particularly after you unfreeze, that suggests you could probably bump your learning rates up a little bit, because you really want to see this kind of shape. It's going to train faster and generalize better. Just a little bit. Right? And you're trying to particularly see it in the validation set, the orange is the validation.
So that's very interesting, because I found that whenever you find, whenever I saw the losses increase and then drop again, I thought it was some sort of issue with the learning rate that we had selected. I didn't realize that it was actually doing annealing to begin with, like it was built into this library. So this is very interesting. It kind of makes me think that my intuition about how like loss should behave is not very accurate, because you can see here, it's 0.91, and then it goes up to 0.912 and then drops again. and according to him, like this is actually
And
okay.
again, the difference between kind of knowing this theory and being able to do it is looking at lots of these pictures, right? So like after you train stuff, type learn.recorder dot and hit tab. You see what's in there, right? Particularly the things that start with plot, and start getting a sense of like what are these pictures looking like when you're getting good results. And then try making the learning rate much higher, try making it much lower, more epochs, less epochs, and get a sense of what these look like. So in this case, we